Alright, hey guys, and welcome back to another AP Physics C video. Today we're going to be using Gauss's law to find the electric field at a radius little r, where little r is greater than 0, but it is less than big R for a non-conducting sphere with radius big R, uniform volume, charge density, and charge plus Q. So let's just jump right into it. We're going to think, in this type of situation, whenever you have like a non-conducting sphere and you're asked for electric field, you should always be using Gauss's law. Gauss's law is says that the surface integral of E dot dA is equal to Q enclosed over epsilon naught. And I'd like to make a small little disclaimer. In the last video, I said line integral the entire time while I was referring to that integral symbol. But what I really meant was surface integral, because a line integral sums up little one-dimensional pieces dl or dr, right? But a surface integral sums up two-dimensional pieces that are dAs. And that's what we were doing in the last video, so I misspoke. Even though they have the same symbol, they're two very different integrals. But the reason why this has the same symbol is because it's connected to the surface integral, or it's connected to the double integral through this thing called Kevin-Stokes' theorem. And if you want to learn more about that, I recommend watching a video on Stokes' theorem. It's pretty interesting, actually. But yeah, that's really all I wanted to say. For Gauss's law, we're always going to be working with the surface integral. When we get to Ampere's law, we're going to be working with the line integral. So knowing that, let's just continue. So we need to know that whenever we're using Gauss's law, we're going to try and surround whatever we want to find the electric field from in a Gaussian surface. So in this instance, we're trying to find the electric field from whatever charge is enclosed from 0 to r. So basically, I said it there, we're going to try to enclose the charge from 0 to r. Here, we don't need to worry about this charge, this excess charge on the edge, because that's not contributing to my electric field at that radial distance r. What actually is contributing to the electric field at the radial distance r, I'll write it in purple, is this charge q prime. So q prime, I'm using the prime notation because it really just means nu, instead of just to differentiate between q and q prime so there's no confusion. But yeah, q prime produces the electric field that is at the radial distance r. So now what we need to think about is, well, q prime is basically the q enclosed. So what I can replace, oops, sorry you guys, can I, okay. What we need to think about is on this right side, q enclosed is really just this q prime, right? Q prime over epsilon naught. So now I have Gauss's law, just kind of tailored to my situation. So now we want to find Q prime. This is where this part, uniform volume charge density, comes in. So we're going to use that. We're going to use that over here, and we're going to recognize that volume charge density has this symbol rho, where rho, when it's uniform, is always equal to Q over V, right? But what rho is also equal to, because rho is a ratio, is q prime. Sorry, I should write that in purple. Q prime over v prime. And the reason why rho is also equal to q prime over v prime is because if I take that bit of charge that I'm enclosing, q prime, and I divide it by the volume that actually encloses that charge, v prime, it'll get me the same, I guess, numerical value that the entire charge, I should do this in a different color, let's do this in blue, that the entire charge, right, sorry, the entire charge would get me, we'll call that blue Q, blue Q, that the entire charge divided by the entire volume would get me, because that's how uniform charge density works. It allows us to have this ratio. So that's enough said about that. But what we're going to do really is rewrite this on the bottom and recognize that this is an algebraic equation, right? So q prime divided by v prime equals q over v. Well, now I want to think, if I want to isolate q prime and I want to solve for q prime, wouldn't I just multiply v prime to both sides? And you'd be absolutely correct if you said that. So now q times v prime divided by v is equal to q prime. And now you might be asking, well, what is v prime? Well, v prime is the volume of the Gaussian surface, or the volume of the volume that corresponds / encloses the charge q prime, right? So Now I want to think, when I'm using a Gaussian surface, we know that every time we use a Gaussian surface, when it's a cylinder or when it's a sphere, it has to be at the radius at which you want to measure the electric field. So what would the radius for V prime be? And if you said it's little r, because we're measuring at little r, then you would be correct. So we're just going to sub in for V prime and V over here, and we're going to say that Q, and the volume of a sphere is 4/3 pi r squared, so now I'm going to use that fact, Q times 4/3, 4/3 pi, and this is not 4/3 pi r squared, I meant 4/3 pi r cubed. 4/3 pi little r cubed, because little r corresponds to V prime, divided by 4/3 pi. And now V is the entire volume, so I'm going to use big R here. 4/3 pi big R squared has to be equal to Q prime. So now I'm going to simplify. I'm going to cancel what I can on the top and bottom, and I get this Q r to the third, little r to the third divided by big R to the third is equal to Q prime. So now I can sub in for Q prime in Gauss's law, and I'll just pull Gauss's law down. So I'll rewrite it down here. The surface integral of E dot dA is equal to, what was Q prime? It's Q over R to the third, little r to the third divided by big R to the third over epsilon naught. And I'll simplify that right side a bit. Q R to the third over epsilon naught R to the third equals this entire good thing. So now this left side looks a little bit more complicated, but our right side is looking a little bit easier because we have it in terms of the given quantities and fundamental constants as appropriate. So this is the fundamental constant, epsilon naught. You don't have to worry about that. You can leave that in there. Usually you're always allowed to leave it in your derivations. As is customary for AP Physics C, but we're going to work with this left side now. So like last time, we had that water bottle analogy, right? Where we had a little pencil inside of a water bottle and all of the electric field lines that radiated from that pencil, if it were to be charged, right, would match up with the dA vectors, the area vectors that came from those little patches dA, give us some symmetry that allows us to bypass the calculus 3, I guess you could say, computations on this left side of Gauss's law. We're going to do the same thing here because we picked a Gaussian sphere, right? We're allowed to say that for every single E, right? For every single E dot dA, the cosine between the two, the theta between the two of them will be 0, which is equal to 1, right? Now, the reason for that is because whenever you have, like, if you can imagine like a soccer ball almost, imagine you put a little tiny bouncy ball inside, one of those, like a gumball even, a little gumball that you get from one of those machines that are like 25 cents. If you put a gumball and you put a soccer ball outside of the gumball, let's imagine the gumball is charged now. If the gumball has charge, well, it kind of acts like a point charge, right? And you know that the electric field lines that come from a point charge radiate radially outwards, so long as it's in free space and there's no other charge near it, right? So that's how this will work. It'll radiate radially outwards. But now I'm going to draw the soccer ball in blue. That's the soccer ball, right? The soccer ball, guess what? The little dAs, I'm going to draw the little dAs in pink. That's it looks two-dimensional like a line right now, but I really can't draw three-dimensional. I really can't draw a sphere on the screen. I'm really bad at drawing. So just bear with me. This is a dA. The dA vector, right? dA, right, will be on the surface of the soccer ball, but the dA vector, I should really say this is the dA vector, will be perpendicular to the surface of the soccer ball. In other words, it will point radially outward. So since both of them point radially outwards, right, they line up, and the theta between them is equal to 0. So now I'm allowed to compute this left side of the integral. I'm allowed to compute the dot product, right? So now I get the surface integral E dA cosine of 0, right? Well, that's what the dot product is, because A dot B is equal to the magnitude of A times the magnitude of B cos theta between A and B. That's what I just did here. That's what I just did here. Since cosine of 0 is always 1, I can simplify this to 1, and in other words, I can really just take it out because 1 times anything is itself. And now I can bring back that right side of the equation, and now I have a something of an easier integral to compute with less vectors. But I know, now I have this E dA. I know that for every single point on this, what's it called? On this radius that is little r, the electric field will be the same, right? Because this has uniform volume charge density, and even if it didn't have uniform volume charge density, so long as the charge density is dependent on radius and not any other thing, for a specific radius, the electric field will be the same along the entire Gaussian surface for that radius, right? It has the same magnitude everywhere. So in other words, it's constant. So I can pull that out of my surface integral, and I can say the surface integral of dA times E is equal to QR to the third over epsilon naught R big R to the third. So now this is looking a little bit more like that Gaussian cylinder like that I was doing earlier. Like you can see, this is basically the same process. You kind of compute the dot product, pull out E. Now you have surface integral dA, and whenever you have surface integral dA, you're summing up little patches of dA for the Gaussian surface. So since we picked a Gaussian surface that is a sphere, we know that this surface integral dA is the surface area, and the surface area for a sphere is 4 pi, whatever the radius. I'm going to call that r sphere, r sphere squared. So it's 4 pi r squared. That's the surface area. But in this instance, what we're taking the surface integral for dA's of is going to be the Gaussian sphere, not the actual like big sphere with radius r. No, because we're visualizing it. The entire point of the Gaussian sphere was to measure the electric field, so we're going to use little r instead of big R there. So now we're going to get E 4 pi little r squared is equal to QR to the third divided by epsilon naught big R to the third. And now all I'm going to do is divide by r squared. Actually, I'm going to divide by 4 pi r squared to get E by itself, because in this problem I just want the magnitude of E, 4 pi r squared, and I get E, the magnitude of E is Q, and now r to the third divided by r squared is just r, so this goes to the first, QR over 4 pi epsilon naught big R to the third, sorry, QR divided by 4 pi epsilon naught times r big R to the third is equal to E. And now I could stop here, but I like Coulomb's law constant, and I know Coulomb's law constant is 1 over 4 pi epsilon naught. That's K. So I'm actually just going to write it in terms of K, because I don't like this 4 pi epsilon naught. I just like KQ R and R to the third. And that is the electric field at the radial distance r. For that non-conducting uniformly charged sphere. So hopefully this helped you guys, and hopefully I explained it well enough. But if you can recognize, this looks a lot like the other process that we were doing earlier. The only difference is that the surface area changed. But just as a recap, what we did was we analyzed the problem that we were looking at, and recognized that whenever we have some kind of electric field inside of a sphere, we really need to visualize a Gaussian surface. And that Gaussian surface will correspond to the surface area later when we use that surface integral dA, right? We just did Gauss's law's procedure where we compute the dot product, the vector dot product, and then we get to, what's it called? We compute the vector dot product, we pull out the electric field, which is a constant for a specific radius, and we compute the charge enclosed, and then we do some algebra, and then we arrive to a final answer. And I'd just also like to make something clear here. The reason why I use this gumball soccer ball analogy is whenever you enclose a charge q prime and it's a sphere, right? No matter what, so long as the enclosed charge is how do you say? The enclosed charge is kind of spherical, it'll act like a point charge almost at that point, right? So if I were to enclose this entire thing, and this, we'll call this radius R2, um, this entire sphere with non-conduct with uniform volume charge density, this whole thing, but a total charge of plus Q, it would just act like this. The electric field would just be KQ over R2 squared. That is it, right? So that's why we're kind of allowed to visualize with this soccer ball point charge analogy, soccer ball, gumball, point charge, Gaussian sphere analogy, right? Um, and that's why the electric field vectors will point radially outwards, right? Because it's a sphere, and you can kind of simplify that sphere down to a point charge because they'll, at the end of the day, they'll kind of act the same, so long as it's being enclosed by a volume that's bigger than itself, or the same as itself, right? So long as the charge enclosed is not the volume, right, that encloses the charge is not bigger than the volume of your Gaussian sphere. Otherwise, what are you doing, right? So moral of the story, your Gaussian sphere should always have a volume or a radius that is the same as where you're trying to measure your electric field. And you should always take Q enclosed and express it in terms of your given quantities, simplify, and then you'll get your final answer. So hopefully that helped you guys. Hopefully it made some more sense. And yeah, I'll catch you guys in the next video.